next one is communication. So any communication we have started with the block schematic for the source, channel and the destination that we are going to have it. And then we have seen what is needed for the modulation. So we have seen that we go for the modulation because we can go for frequency multiplexing. Then the effective radiation that we can have it by having the required radiation sites, the narrow band and common processing. So these are the series for the modulation that we are going to have. Our advantages for frequency translation. So what is this frequency translation? So we have seen that when we have this baseband signal, we have migrated our frequency translated to higher frequency of a carrier, so that we have put this baseband signal onto a carrier with a high frequency signal. And we have seen the spectrum of this frequency transfer signal and how it is going to be. So a normal frequency translation that we have seen is going to be a linear one that we are going to have it. So if the spectrum in the baseband signal contains two spectral lines, then we have seen that it is going to be double. So if we have 6 spectral lines, then we have seen that cell lines and so on. Whereas if we have this 0 to FM, the baseband signal with the frequency component to be highest frequency component of FM, then we have seen that the frequency translated signal will be having the frequency components from FC minus FM to FC plus FM, so that 2 FM will be the bandwidth that we are going to have. So that's what we have seen for this frequency translation. And in this frequency translation, what we have done is we have multiplied the baseband signal VM of t with that of the VC of t. So we have this VM of t, which is going to be VM cos omega m of t, and we have multiplied this with VC of t, which is going to be AC cos omega ct, where omega m is 2 pi f and omega c is 2 pi fc that we are going to have it. So when you multiply these two, we have got the signal AM AC cos omega mt into cos omega ct. The spectrum of this baseband signal is at FM and minus FM, whereas the spectrum of the carrier is at minus FC and plus FC that we are going to have it. Whereas the frequency transfer signal will be having FC minus FM and FC plus FM and minus FC plus FM and minus FC minus FM. So these are the frequency components that we are going to have it with this FM and FC minus FM, when we have the carrier frequency of FC and the modulated frequency of FM that we are going to have it. Then we have seen that if we have an arbitrary modulated signal with a spectrum like this, with 0 to FM, then the frequency transfer signal will be having a spectrum like this, with the center frequency being the carrier frequency that we are going to have it. In this we have seen the what we call the amplitude modulation, where we said that the amplitude of the carrier is going to be changed in accordance with the instantaneous amplitude of the baseband signal. So what we have is the DAM of t. We can put it as AC into 1 plus KAM of t cos omega ct, where K is the amplitude sensitivity of the modulator that we are going to have it. And we have is going to be limited to less than or equal to 1 that we are going to have. The magnitude of your KAMT we are limiting to less than or equal to 1 that we are going to have it, so that at any time AMT magnitude of this will be 1 plus or 1 minus the value that we are going to have, so that the values of this positive side will be always positive only. Similarly, when cos omega CT is negative, always this negative will be in the negative side that we are going to have it. Therefore, if you have your baseband signal, M of t something like this, about modulated signal, because we are having 1 plus and negative signal will be having a signal like this, 1 plus KMT, cos omega is positive, you are going to have this value, and cos omega is negative, you are going to have this value. So in between you have this carrier frequency, which is going to be very high frequency that we are going to have it, compared to our baseband signal M of t. So this will be the modulated signal waveform that we are going to have it, with the spectrum being with this, with a carrier at f of c and carrier at minus f of c also will be there in the spectrum, because what we are having is, this is going to be AC cos omega CT will be there, and you are going to have AC KMT cos omega CT. So AC cos omega use those two spectral lines at FC and minus FC that we are going to have it. Whether this KMT cos omega CT frequency translated spectrum. So that's why we are having this signal in the frequency domain that we are going to have it. So this is what our AM signal that we are going to have it, considering that we are having a generic signal M of t that we are going to have it, which is having the frequency components from 0 to FM that we are going to have. Suppose if you say that we have only the signal as AM cos omega is MT, that is a single tone frequency signal that we are going to have it as your baseband signal, then your AM signal will be equal to for your signal single tone, we can say that M cos omega MT into cos omega CT, where M I open that K into the magnitude of your omega MT, or this K into AM will be equal to your M, the modulation index that we are going to have. Therefore, with this variation, this waveform that we are going to have it will be a sinusoidal signal that we are giving. Therefore, your waveform will be looking like this. Instead of a general waveform, you are having a sinusoidal signal. This will be the modulated signal that we are going to have it with. This is the baseband signal, and this is our carrier frequency signal that we are going to have it. So in this one, we are having this is the maximum signal that we are going to have it, and this will be the minimum amplitude that we are going to have it in the positive side, right? A max and a minimum that we are going to have it. So what will be A maximum? A maximum will be when you have cos omega CT equal to 1 and cos omega MT equal to 1, so that your A maximum will be equal to AC into 1 plus M But I minimum will be equal to AC into 1 minus M. Okay. So this is the relation between your maximum value and minimum value that you are going to have in your modulation waveform. So once you have this A maximum and A minimum, you can obtain what is going to be our modulation index. So this you can calculate as A max minus A min by 2AC, or this is equal to A max minus AC by AC, or A max minus A min by A max plus A minimum, or this we can write as AC minus A minimum by AC. Whatever the values that have been given, you can calculate accordingly the modulation index of your signal that we are going to have it. So if you are given only AC minimum and AC, again you can calculate what is going to be the modulation index, or A maximum and A minimum only are given, you can use this equation. So depending on the information that has been given, you can calculate what is the modulation index, or if you multiply this with 100, that will be our percentage of modulation in our AM signal that we are going to have it. So we are going to have this variation that we are going to have it with the singleton modulation that we are going to have, and here if M is going to be greater than 1, then the waveform will be of different nature, and we will see that when we are discussing about the maximum allowable modulation that we are going to have it. So before that, we are having this VAM of t is AC cos omega CT plus MAC cos omega CT into cos omega M of t. So this is the signal that we are going to have it. And what is the signal? This is the carrier signal. And this is your omega CT into omega MT. That is the frequency translate signal that we are going to have it, which are called our sideband signal. Because we are going to have the two frequency lines that we are going to have it. So you are going to have this FC plus FM, the upper frequency, and FC minus FM, the lower frequency. So where is the information that we are having? What is the information? Your baseband signal. Whereas this carrier doesn't carry any information. It's only the information that is available in the sidebands. So your content is going to be there only in the sidebands, but not in the carrier signal that we are going to have it. So what will be the power relations that we are going to have it for this one? So if we have this your VAM of t is going to be AC cos omega CT plus KA M of t AC cos omega CT into cos omega M of t in a general modulating signal M of t. So as you are saying that the information is available only in this, whereas this is a simple carrier that we are going to have, which is contains no information. So what will be the power relation between the different components of your carrier and the sideband that we are going to have it? So what will be the carrier of this AC cos omega CT power? The carrier power, if you say that this we are allowing to a 1 ohm resistor, what will be the carrier power? The PC for AC cos omega CT. Cos omega CT is the signal that we are going to have it. So what will be the power that we are going to have it? This you already calculated in signals and systems. Power of AC cos omega CT. So this is going to be 1 by 2 AC square. The magnitude square is half of the magnitude square of our sinusoidal signal that we are going to have it. Okay. Uh, Here there is no cos omega m of t. So because I have put m of t, so m of t cos omega ct. Okay. So what will be the power on this side band? Because this is multiplied with cos omega ct. This is the magnitude. So half of the average value of the signal. So your sideband power will be equal to half of. I will assume that K equal to 1. The amplitude density I am assuming to be equal to 1, so that this will be half of AC m of t average square. Here we have that AC square, average square. And now we are having this as AC mt whole square. The average power that we are going to have it. Or this we can write as 1 by 2 AC square average. Therefore, if you calculate the relation between the total power and the sideband power, what is the total power? The sum of the carrier power and the sideband power. So your PT will be equal to PC plus PSB. The efficiency of this modulation, we can have it as P sideband by P total into 100%. The efficiency in the percentage is going to be the sideband power, which is going to be the information that we are going to have it by the total power that we are transmitting into 100. Therefore, this will be equal to 1 by 2 AC square average of this by 1 by 2 AC square plus 1 by 2 AC square m square t average. Therefore, this will be equal to average by 1 plus m square of t average. Mean square, average mean square value. So m of t is a general waveform that we are going to have it. The efficiency is going to be m square t by 1 plus m square t average values. So this is for a general signal. Suppose if you say that this is going to be like this single tone signal am cos omega mt with the modulation index is equal to m, then what will be this value when this is going to be am cos omega mt? Then the expression is going to be 1 plus m cos omega mt. So instead of mt we have m. So m cos omega mt average value you have to find out. Therefore, what will be average value of this m cos omega mt? The power of this m cos omega mt. Power of the signal m cos omega mt. Pardon? Power of this AC cos omega c, it is half AC square. So this will be m square by 2. Therefore, with this single tone frequency, the efficiency that we are going to have it will be equal to m square by 2 plus by m square by 2. Right? Therefore, this will be equal to 1 by 2 plus m square into 100 if you want to have the percentage. The efficiency value is going to be 1 by 2 plus m square, where m is the modulation index. Right? Therefore, here m we are saying that it is less than or equal to 1. Or your k m is going to be less than or equal to 1. Suppose if m equal to 1, that is maximum modulation index that we are keeping is 1 or 100% modulation. Then what will be the efficiency? 1 by 2 plus 1 or 1 plus 2. Okay, because m square equal to 1. Or this is going to be 1 by 3. That means efficiency is only 33.3% that we are going to have it. That means where is the remaining power? What is eta? The P sideband by P total. So remaining 66.7% is going to be our carrier signal. And this carrier doesn't have any information content except carrying the information signal that we are going to have it, but doesn't carry any information. Therefore, 66% of your total power is a waste that we are going to have, whereas only this 33.3% is going to be our information content that we are going to have are the two side bands. As I said that we have this waveform. This FC to FC plus FM, we said it is the upper side band, and FC to FC minus FM, we said the lower side band. Similarly, this is going to be our lower side band, and this will be our upper side band. That means you have the two side bands. One sinusoidal signal cos omega c minus omega m, and another one is cos omega c plus omega m of t that we are going to have it. So two side bands we are going to have it. So your entire power information that we are going to have it is only in these two side bands, right? So half of that will be there in each side band that we are going to have it. That means each side band will be having, if you have m equal to 1, this 33.3 by 2 that we are going to have it. Okay? So this will be the power content that we are going to have it in each of the side bands, that 33.3 by 2. Whereas that 66.7 is going to be our carrier power that we are going to have, which we are using only to carry the information that we are going to have it, which is doesn't contain any information, whereas the entire information is there in your two side bands that we are going to have it. So when we say that if you are going to have it, the signal as 1 plus m cos omega mt into cos omega ct with a single tone modulation frequency that we are going to have it, then we are going to have the signal as AC cos omega ct plus MAC by 2 cos omega c plus omega m of t plus MAC by 2 cos omega c minus omega m of t. This is the signal content that we are going to have it. Therefore, PC is 1 by 2 AC square. And what will be our P upper side band? 1 by 2, 1 by 4, m square, s square. So this square by half, because this is sinusoidal signal. So m square s square by 4 by 2. Therefore, this is going to be 1 by 8 m square s square. And this will be equal to your lower side band power also. Therefore, your total side band power will be 1 by 4 m square s square that we are going to have it. So that is just the power relations between your and our side band signals that we are going to have it. So we will be asked to calculate any of the things given the values. Okay? So find your own problem and see that how we are going to solve for your power calculations and the modulation index that we are going to have it with A maximum and A minimum also. The values that we are going to have it. Anyhow, the concerned mentors will be giving you the assignments to calculate these based on your A max and A minimum and the carrier power and the modulation indexes that we are going to have so that you can calculate. Suppose if you say that M equal to 20%, instead of M equal to 100%, we have put M equal to 20%. Then in each sideband, you are going to have only 1% of the power. If M equal to 20%, each sideband will be having a maximum of 1% of the total power, because this is 0.2, so 0.2 square by the total power, which will be equal to only 1% of the total power that we are going to have it, each sideband. So that means remaining all is going to be our carrier power only. That's why the modification of this we are going for our suppressor carrier modulation and then single sideband also. We'll see that at a later case. Okay. So as far as the AM is concerned, these are the relations between your modulation index and the total power that has been carried. So when you say that amplitude modulation, you are having both carrier and the two sidebands that we are going to have. This is what we are going to have, the carrier and the two sidebands that we are going to have it. So this is about your single tone modulation. Similarly for the double tone, you are going to have the average value of this M square T that we are going to have it. Okay. So based on that, the modulation indexes we have to calculate accordingly. Whether they are having a multi-tone or single tone or whatever the signal that we are going to have it. So these are the relations between your modulation index and the total power that has been transmitted, along with your A max and A minimum with the modulation index that we are going to have it. So this is your amplitude modulation, how we are going to have the different side bands and the total power that we are going to have it. Right? Any doubts so far? How we are going to calculate different values that we are going for next for the generation of this amplitude modulated signal. So this is about our modulation of amplitude by going for the different modulation indexes that we are going to have it. Normal modulation index that we are going to have it is around 30 to 50% is the transmitted signal that we are going to have it in your modulation. Anyhow, that we will see and we are discussing about transmitters and receivers that we are going to have. But never we will go for this 100% modulation that we are going to have it. Okay, because that may be giving you the more sideband power, but we will have the limitations on. Okay, so this is about the different theory about the amplitude modulation. Then how to generate the amplitude modulated signal? What is that? We are having the baseband signal and the carrier signal. So how much carrier I have to put? We will see that what are the limitations that we are going to have in relation between our maximum frequency of the baseband signal and the carrier frequency that we are going to have it. But we are having now a source which generates the carrier signal and a source which generates your baseband signal or the modulating signal. So in your modulator, we are having in the AM modulation, we are going to have a switching square law modulator and a switching modulator that we are going to have it. So we have two types of generation of the modulators, the square law modulator and switching modulator. Two modulators, right? The square law modulator, the second one is the switching modulator that we are going to have it. So let us see first the square modulator.
So this will be having a combination of these two signals, the carrier signal and the baseband signal or the modulating signal. So we have a circuit to combine these two, the carrier signal and the baseband signal. Then we are going to have a nonlinear element, as we are saying the square law. So we require a nonlinear element that we are going to have it. So what is the nonlinear device that we are going to have it? A diode is a nonlinear element, a transistor, anything more? Your FET also. So we can use either a FET or a transistor or a diode. Okay. So we are having a nonlinear element that we are going to have it. Then the third element that we require is a band pass filter or a tuned circuit that we are going to have it. A band pass filter, because we have to eliminate other frequencies except these two side bands along with the carrier signal that we are going to have it. So we are going to have a band pass filter tuned to our center frequency. So you are having a tuned circuit. You may be having a single tuned circuit or a double tuned circuit that we are going to have it. Go next. So this is a typical square law modulator that we are going to have it. So we are having the baseband signal M of t generator and the carrier frequency generator AC cos omega CT. These two are combined, added, and then we are having a nonlinear device, the diode or transistor or the FET that we are going to have it. Then a single tune circuit I have shown here to have our band pass circuit that we are going to have it. You may have a double tune also to have a center frequency exactly and then get the required transmission bandwidth that we are going to have it. Okay. So typically this is the circuit diagram for a square law modulator that we are going to have it. So we are have what is V1 of t? V1 of t is the combination of this signal M of t into cos omega CT that we are going to have it. Because these two sources were added with M of t and AC cos omega CT. So this is V1 of t. And let us say that your nonlinear characteristics of the device is going to be some A V1 of t, V2 of t is A V1 of t plus B V1 square t. We are having a second order nonlinearity we are considering, so that your operation of the characteristics should be operated on the nonlinear characteristics of your diode or the transistor, with the typical characteristics being A V1 of t plus B V1 square t that we are going to have it between the input and the output of your nonlinear device. And we have seen that V1 of t is this M of t into cos omega CT. Therefore, what will be our V2 of t? A into M of t plus cos omega CT plus B into M of t plus AC cos omega CT square, because we are considering only the second order nonlinearity. So we are operating our device in this manner, so that we will be having the required output after the band pass filter or the tuned circuit. So this we can write it again as A into AC cos omega CT plus A into M of t plus B into M square t plus B into AC square cos square omega ct plus 2B AC into cos omega ct. Therefore, this will rewrite as AAC into 1 plus, because this AAC cos omega c we have taken, and where is the other cos omega ct? In this way, we have 2B AC cos omega ct. Therefore, this will be equal to 2B by A, into M of t also, because this is A into B. 2B M of t AC cos omega ct, right? Therefore, this is 2B by A M of t into cos omega ct. The first and last terms are combined here. So remaining terms are A M of t plus B M square t plus B AC square cos square omega ct. This is what our required amplitude modulated signal. 1 plus Ka M of t cos omega ct, where Ka equal to B by A here, where A and B are the constants, arbitrary constants that we have chosen for our download of the transistor characteristics. Therefore, your Ka, the amplitude sensitivity of your modulator is now is going to be 2B by A, right? Giving this equation, A and B are given, so you can calculate that value. So these are all the unwanted frequencies that we are going to have it. So by passing this to a tuned circuit centered around this omega c, we can eliminate all other frequency components that we are going to have it. So if you draw the spectrum of this, output before the band pass filter, that is V2 of t, V2 of f will be so this is your A into M of t, the baseband signal, plus B into M square t. When it comes to square, that means you are going to have the second harmonic. Therefore, from FM to 2FM you are going to have it to minus 2FM, and square of this. So this is your M of f, and this is your this spectrum is for M square t spectrum. This is for M of t. So M of t is between minus FM and plus FM, whereas M square t is minus 2FM to 2FM. So these two have been taken care. Then what is this AC square cos square omega ct? That is a DC signal plus 2 omega ct. That is a 2FC you are going to have it somewhere away. Minus 2FC. And what is this signal? This is our required modulated signal centered around FC. So this is minus FC and this is plus FC. Your carrier at FC and minus FC and your modulated signal. So this will be the spectrum of your V2 of t. By passing this through a band pass filter, a tuned circuit, we are eliminating all other frequency components, right? What should be the constants on this FC value in response to your FM value? What will happen? This point will be equal to 2.5 FM minus FM, because this is FC minus FM. That means this point will be of 1.5 FM, whereas your M square T goes up to 2 FM. That means there will be an overlap here. Whereas if it is going to be at least 3 FM, FC is going to be at least 3 FM, then this point and this point will just touch. That means your carrier frequency FC should be always greater than 3 FM in your square law modulator. The carrier frequency should be at least greater than 3 FM. In practice, anyhow, we are going to keep much higher frequency for the carrier, but theoretically, the limitation for your carrier frequency is going to be 3 times that of your FM that we are going to have it. Okay? So this is how I will be having a square law modulator to generate all these frequency components that we are going to have it, and then get the required carrier and the 2 side bands or your amplitude modulated signal that we are going to have it. So that is about our square law modulator. Then what will be our next generator that we are going to have it? So as you said that the one is switching modulator. So this is our typical schematic for your switching modulator. Again we are having this modulating signal and the carrier signal. The generators that we are going to have it, and put onto this your diode circuit, and then you are having your resistor to get the output that we are going to have it, with the required filtering and other things that we are going to have it. The band pass filter you have to have it at the output of this resistor. So after this resistor, after V to 2 T, we are going to pass this to a band pass filter once again to eliminate all the frequencies except your carrier and the 2 side band frequencies that we are going to have it. So what should be the characteristics of your diode? So here we are assuming that the carrier signal CT is very large compared to your baseband signal amplitude M of T. CT is going to be very large compared to your baseband signal amplitude M of T. Therefore, your switching characteristic of your diode depends on the amplitude of your carrier signal C of T, right? Because your M of T is very small, so carrier amplitude is going to be controlling the switching characteristics of your diode. And we are going to assume that the diode is going to be an ideal diode. What do you mean by ideal diode? Ideal diode. Sharp? What do you mean by sharp? Ideal diode. So which is having a 0 forward bias resistance and infinity reverse bias resistance that we are going to have it. That means a typical diode characteristics will be something like this. For negative values, it is 0, and once you are having positive, you are having full current that we are going to have it. Right? This is the resistance characteristics of our diode. Ideal diode characteristics, if you plot it, input and output. For negative, the value is 0, and for positive, the resistance is 0, right? Therefore, what will happen? For CT greater than 0, the diode is forward biased. Right? Because we have said that your switching characteristic depends on your carrier voltage only. And for CT less than 0, the diode is reverse biased. No current. That means the CT is going to control the on and off your diode. So when we have this diode off, the output when CT is less than 0, the diode is reverse biased. So what will be the output? 0, because there is no connection between the input and output. V1 of t and V2 of t, there is no connection, because this is reverse bias, infinite resistance is there, therefore it is an open circuit. Whereas when CT is greater than 0, the positive amplitude, then the diode is conducting, or it is having 0 resistance. Then what will be the output? What are the input you are going to have? M of t plus cos C of t. Both will be appearing across the resistor as V2 of t, that way are going to have it. Therefore, for C2 of t, positive and negative, you are having a switching characteristic of our diode to get the required output V2 of t for 0 and a combination of the baseband signal and the carrier signal, that we are going to have it. That means if CT is greater than 0, V2 of t is V1 of t, which is nothing but AC cos omega CT plus M of t. For CT less than 0, V2 of t is 0, right, because it is negative. The diode is reverse biased. Therefore, we can write this for any signal M of t plus AC cos omega CT into some gate function GP of t. So this GP of t, the pulse signal, is going to be having equal amplitude on and off periods, that we are going to have it. No, previous. Wait. So this is the pulse signal that we are going to have GP of t. So I am multiplying this M of t into AC cos omega CT with this pulse on and off period, that we are going to have it, and equal on and off periods, because CT of t is positive or negative in the cos omega CT, the carrier signal, equal periods. So you are having equal rectangular periodic signal, that we are going to have it. And the relation between this V1 of t and V2 of t is given like this, a linear diode characteristics, that we are going to have it. If you write a piecewise linear combination, that we are going to have it as V1 of t varies, V2 of t also varies with a slope of 1. The input and output V1 of t and V2 of t relation, the previous slide that we are going to have, that is the one that we are going to have it to give you the V1 of t and V2 of t. As V2 of t, V1 of t changes, V2 of t changes. For the CT greater than 0, CT less than 0, no output, right, because diode is off. This is for CT greater than 0, positive, slope 1. What are the input you are going to have it? You are going to get the output. Whereas for CT less than 0, the output is 0, that we are going to have it, right. Therefore, we are having this as our switching signal that we are going to have it of your m of t plus c of t. So how to get your, and this we are saying that this is the circuit for your amplitude modulation. So how to say that we are getting the output of AC into 1 plus m of t cos omega ct that we are going to have it, and what are the other frequency components. So this is your required signal m of t and cos omega ct, and this is the GP of t which are shown here. So what will be your GP of t when you expand this as a Fourier series? A pulse train that we are going to have it. So this will be having one by 2 plus 2 by pi sigma minus 1 to the power of n minus 1 by 2n minus 1 cos omega ct into 2n minus 1. Therefore, back to our signals and systems again, right? That's what I said to you when we are discussing signal system. That will be the basic course or the foundation course for all our communication courses that we are going to have it. So this is your expression for our pulse signal that we are going to have it with equal on and off the one that we are going to have it. Okay? And anyhow, verify this. Again, going back to our signal theory. So this is your GP of t, which are multiplying with this m of t plus cos omega ct. Therefore, your V2 of t will be equal to m of t plus AC cos omega ct into your GP of t 1 by 2 plus 2 by pi sigma 1 to infinity n minus 1 cos omega ct into 2n minus 1. This is your U2 of t. The mt plus ct expand. You are having this 1 by 2 of m of t plus AC by 2 cos omega ct. The product is the first term plus in this summation I will expand this for n equal to 1. When n equal to 1, what will be the value? This will be equal to 2 by pi into m of t and because 2n minus 1 is 1. So this is going to be 2 by pi m of t into cos omega ct. N equal to 1 into m of t. And n equal to 1 into AC cos omega ct gives you 2 by pi AC into cos square omega ct. Okay? I expanded this first term into these two and one of this term into these two. Remaining things all I will keep the same. M of into 1 by 2 plus 2 by pi. No, this 1 by 2 also will go. By pi sigma n equal to 2 to infinity. Instead of 1 to infinity, 1 we have extracted already. So we are going to have 2 to infinity minus 1 to the power of n minus 1 by 2n minus 1 into cos omega ct into And here we are having so this will be equal to AC by 2 into 1 plus 4 by pi AC m of t into cos omega ct. These two I am combining, right? AC by 2 into 1 plus 4 by pi AC into m of t cos omega ct plus 1 by 2 m of t plus 2 by pi AC cos square omega ct plus the other term, the product. So this is our required amplitude modulated signal. Cos omega ct. Right? And this half m of t, the baseband signal, but this is cos square omega ct, that is 2 cos omega c plus the DC term. And this will be always m of t into cos omega ct plus when n equal to 2, what will happen? This is cos 3 omega ct, third harmonic, and n equal to 3, this is fifth harmonic, all odd harmonics 3, 5, 7 and so on. All higher frequencies only are having much higher than your 2 omega c. This 2 cos square omega ct is giving 2 omega ct, whether this is giving 3 omega. With the carrier frequency of omega c, then all these frequency components will be going along with this baseband signal half m of t also, because if you look into the spectrum, so this corresponds to this half m of t, and this cos 2 omega ct, so that this 2 by pi AC 1 by 2 will be the impulse at omega equal to 0. And what other frequency are going to have it? This term Fc minus Fc carrier. This one correspond to this. Then minus Fc. Yeah, because of cos square omega ct. So because of cos square omega ct, you have these two, and then DC term. And because of this, we are going to have cos 3 omega ct, 5 omega ct, and so on. And with the product also. When you have this cos omega ct, 3 omega ct, and cos omega ct product, 3 minus 2, 3 minus 1 gives you 2 omega ct. So all of the frequency components, 2 omega c, 3 omega c, 4 omega c, 5 omega c, and so all the higher harmonics are going to be available here. With the required modulation also, when you have cos omega 3 ct into m of t, you are having a frequency translate signal at 3 omega c or 3 fc, that we are going to have it. So all those things will be eliminated by passing this through a band pass filter. So this baseband signal has been eliminated, and all high frequency components also are eliminated in this band pass filter through. So what is the output? Only this component the entire all these frequency components are eliminated to your band pass filter. So after this resistor in the circuit, you put a band pass filter so that you'll with a frequency density of Ka equal to 4 by pi AC. Whereas there we have got 2B by A. So depending on the requirements, we will be having the different variations that we are going to have. Either a square law modulator or a switching modulator that we are going to have. Okay. So at both the places we are using a nonlinear element, the diode or the transistor that we are going to have. One thing is in this square law, the switching modulator, we are going to have only the diode because we want a ideal diode to be represented. We are going to have. Whereas your square law modulator, you can use any of the non-linear elements having a second order non-linearity that we are going to have. So let us say that you have a typical example of a FET square law modulator. So let us say that the circuit diagram for your this is your M of t and this is your AC cos 2 pi f c t. Or AC cos omega c t. So we are having a signal like this. So here we are having Vg. So typically we can say that this Vg is 1 by 2 of M of t plus AC cos omega. The input signal that we are going to have is M of t plus AC cos omega ct. The two signals that we are combining. What will be the output voltage here? This we are taking as a second order linearity. Therefore, the output that we are going to have it will be the output current IDS. What we are going to have it is going to be this gate voltage plus the pinch off voltage square that we are going to have it. Therefore, what will be IDS? From K into proportionality constant for your FET characteristics that we are. This region we are going to operate only in a region that we are going to have it with the required voltage variations, peak voltage and pinch off voltage and the VG voltage that we are going to have it. Okay. So this corresponds to different VG voltages and this corresponds to our pinch off voltages that we are going to have it. So that will be equal to what is VG? So by 4 M of t plus AC cos omega ct by 2 plus Vp so we are going to get M of t plus AC cos omega ct by 2 and square of this other terms that we are going to have it. Okay. So M of t plus AC cos omega ct will be that's what we want as the output. AC cos omega ct, the combinations that we are going to, when you square this, the double term we are going to get. So we are going to get when you have this M of t by 2 plus AC cos omega ct by 2, the first term plus 2 AC we have to get. So we are going to get this M of t plus AC cos omega ct by 2 whole right plus Vp square plus M of 2 plus Vp square already we have put it. So when you square this again, M of t into AC cos omega ct will be coming, right? And already we have this AC cos omega ct in the output that we are going to have it. So similar to this, we are going to get VAM of t equal to some constant into 1 plus some beta M of t into cos omega ct plus the higher order terms and the baseband signal also, right? Which are your output is going to be this voltage. And what is this voltage? V naught of t. If I put this as V naught of t equal to VDD minus RD into IDS. So this is your IDS. A DC component again you are going to have it. You know that you are going to eliminate through this band pass filter. Finally, what we are going to have it is the baseband signal and the carrier signal product that we are going to have it. So by passing this to a band pass filter, we will be able to obtain the required amplitude modulation by using the square law characteristic. That we are going to have. Okay. So this is a typical example that we can say. So you can use any of the transistor, diode or the FET as the square law modulator. Whereas for switching we are going to use only the diode because we have to have the certain operation for CT greater than 0 and less than 0 we have to get a ideal characteristics switching on and off that we are going to have. Otherwise we will be having other frequency components also which gives you the distortions for the other variations that we are going to have. Okay. So that is about your generation of the amplitude modulation by using either square law modulator or that of the switching modulator that we are going to have it. modulation, we are transmitting it. Okay, so that's what we are having, the transmitter, we are having the source that we are modulating it or the frequency translating it, and we are having your amplitude modulation by using either square law modulator or the switching modulator that we are going to have it. Then what you are putting, this you are putting to your antenna system. Anyhow, to get your required amplification and so on, you are having the different processing techniques in your total transmitter system along with the modulation. So we have achieved all those things and put onto the channel. So what is that we are doing? It is we have all that process that we are going to have it, and finally we have to detect the baseband signal M of t. So we are going to have what you call the demodulation process that we are going to have it. Or detection of your baseband signal that we are going to have it. Either we will be having calling as a demodulation, because we are having a modulation at the transmitter. Opposite to that, we want a demodulation, or we want to detect the signal in the presence of the carrier that we are going to have it. So all what are that we can get back the original signal M of, because M of t is our information, not your carrier frequency that we are going to have. So we have to get back the M of t signal that we are going to have. So what are the different techniques that we are going to have it? So we are having pardon, a demodulator. Envelope detector, second is square law detector, third one is detector. Okay, so we will be having an envelope detector, a square law detector, or a rectifier detector that we are going to have it. So let us see that first one as the square law detector, the envelope detector. So we are having another element, again a diode and an RC combination circuit that we are going to have it, which will be using as envelope detector. The input for this circuit is going to be our modulated signal or your AM signal that we are going to have it, VM of t that we are give it as the input signal. So what is the AM signal that we are having? So we are having, this is what our signal, input signal that we are giving to your envelope detector, right? Next slide. So we are having the AM signal as given to your input of the envelope detector, right? And we'll assume that the source for which we are giving is having very minimum resistance that we are going to have. Source resistance RS is very small, or ideally it will say that it is going to be 0. RS we are saying very small, so that your envelope detector will not load any of your source circuit that we are going to have it. Okay, so we want the input of your source should be having very low source resistance that we are going to have it, RS. That's what we are assuming for our envelope detector that we are going to have. So we are giving this out input to our envelope detector. What will be the output that we are going to have it? So for the time being, let us say that we don't have any resistance. So this is your VAM of T, and we have the capacitor. So as the signal goes into the positive direction, the diode conducts. Okay? When the input raises to positive, the diode conducts. And what will happen? The capacitor starts charging. So it has come up to this point. Right? But whereas the input decreases now, because you are having a negative cycle, reduction and then going up to negative cycle. Then again it comes to here, you are having more than this capacitor voltage, then the diode conducts, starts conducting. That is, if this voltage is going to be more than this voltage, then the diode starts conducting. But what will happen in this during this period? The capacitor has to discharge. But where is the path for this discharge? It is reverse biased now, because this voltage is less than this voltage. This is reverse biased. Therefore, there is no discharge. Only some leakage may be there. But ideally, whatever the voltage you are having across the capacitor, it is going to remain the same. That means this voltage remains the same without any discharge. Once it comes to the positive, then again it charges, then it maintains. If it maintains, what is going to happen? When it comes here at no point, this is going to be the same. That means it's not following your baseband. This is your baseband signal. Baseband signal variations have to be followed. For that, we are providing a discharging path. A resistance we are adding for this circuit. So when this input raises, the capacitor charges. But once it starts into the reduction or reducing the input signal, then the capacitor charges starts discharging. Instead of keeping constant when there is no resistance, we have said that this is the output. But if it is not discharging, we are not getting these variations. That's why we want to have a discharge also. That's why I am providing resistance R. Now when this input is less than this input voltage, capacitor voltage, the capacitor starts discharging through your resistance. So some voltage decay will be there. Then once the input increases here and it comes here, this capacitor starts charging. And when the input reduces, the capacitor starts discharging. Then again it charges, discharges, and so on. So what is the output across this point? This is the output. A sawtooth waveform. But the normal output will not be having this much variations that we are going to have it, because your FC is much larger than your baseband signal. We said that 1000 kilohertz or more, or 100 kilohertz. Therefore, this much variation will not be there in the actual practice. It may be something like this. Following the waveform. This envelope is coming like this. Then you pass this to a low pass filter, and all this variations because these are all high frequency components at the carrier frequency will be eliminated because this is at the 2FC you are going to have it, these spikes. So in the path is to another filter, low pass filter, all this will be going and then you are going to get a smooth output waveform which is nothing but the envelope of this, which is nothing but your baseband signal M of t. The envelope of your amplitude signal, amplitude modulated signal is nothing but your baseband signal. So we are having this signal which is nothing but your M of t, and because this is corresponds to envelope of your input signal, we are calling this as envelope one detector circuit that we are going to have it to demodulate your amplitude modulated signal. What are the constraints on this circuit that we are going to have it? R and C. We have a time constant R into C, right? So how much R and C you have to put? We said that the source resistance we want it minimum as much as possible so that it charges fast. So RS into C, we want this very, very small, and this discharging should be along with your baseband signal. So what is this baseband signal? FM. What is the time that we are going to have it? 1 by FM. So this RC should be less than 1 over FM, so that this will be having following this waveform. Otherwise, it will not be charging and discharging. Similarly, this 1 by FC should be less than your time constant RC, so that this is going to follow the variations in the carrier frequency that we are going to have it, right? And that's what we are having. 1 by FC should be much less than your time constant, and this time constant should not be greater than 1 over FM also. Otherwise, you should not be following your variations in the baseband signal. So you have designed your resistance and capacitance such that based on your carrier frequency and your baseband signal frequency that we are going to have. So this is the simplest circuit that you can have it as AM detection that we are going to have it. A simple diode and RC combination along with some filtering to eliminate your high frequency carrier harmonics that we are going to have it, so that you are going to get only the required baseband signal M of t that we are going to have. Okay, so that is one method of AM detection that we are going to have it. In the next class, we will discuss about the square law detector, rectified detector, and other variations that we are going to have. Any queries? Okay, so the mentors can mail the information that we are going to have it. If any queries are there, we will answer that one. Right? Hello?
Hello, Aditya College, can you please respond?
Hello?
Yes.
Hello?
Yes, sir, please speak. What is your question actually? Sir is waiting here.
Hello? Hello, yeah.
Yes, speak.
Our voice is audible, sir?
Yes, yes.
Sir, you're explaining about sir, you're explaining about the singleton modulation,
Yeah.
but what about the multitone modulation, sir? Hello?
Multitone modulation we have
Hello?
seen, na? Yes. Multitone modulation also has heard M of T, a typical signal between 0 to FM. The multitone single tone signal we have calculated only to calculate that power relations between the input and output. Variations, we have discussed that. Hello?
Yes.
Are you able to hear me?
Hello? Sir. I hear me, sir. Please, sir.
The single tone
Hello?
calculations. The
Hello?
single tone
Sorry,
modulation
the voice
calculation.
is not audible.
Hello? So far, have you got the
Hello?
audio? Video both. Previously.
Yes, sir. Yes, sir.
I am hearing now.
Your voice is audible, sir.
Okay, then
But it is cutting down, sir.
check up our audio. Okay, all others are getting. So we have discussed the single tone modulation to have the relation between the power relation between the sideband and the carrier powers. Whereas for the multitone signal between 0 to FM, we have seen the different modulations already available at the waveforms that were given with the spectral lines. So this is what for your single tone. Whereas we have this all the frequency components. We are having a spectrum like this. The first half, the single tone spectrum of the baseband signal, and this is the modulated signal. Whereas this is for the multitone, 0 to FM, all the frequency components are the typical audio signal. Then we have the modulation. Hello?
Sir, it is hello?
That's fine. Hello?
Sir. Hello.
Yes? Aditya College?
Hello.
Faculty College?
Sir, you can continue, sir. Hello.
Anyway, we are signing off for today. Okay? We'll meet again on Monday. Right. You can doubt on here.